All right, so now we know valence electrons. We also know that atoms are most stable, or we can say that they want, right? It's not that they actually want, but it's just their most stable form, a filled valence shell. This is often called the octet rule that I'm sure you've heard about before, right? And so metals, they have some options, right? So if we take a look at like lithium or sodium, right, they have one electron in their outermost shell, and so they need to get to a filled valence shell, and that'll be 8 valence electrons. And so one option maybe that you could think of is that they gain 7 electrons, but that's quite a lot of electrons to take, and so that's very hard to do, and so that's not going to happen. And so instead what they kind of do is they kind of cheat a little bit, and to have a filled valence shell, they just lose 1 electron, right? If sodium loses its valence electron, it has a filled valence shell because it's got all of these electrons. And same thing with lithium. If it loses its 1 valence electron, its valence shell is filled. And so they kind of cheat a little bit. And so that's why we get lithium plus and sodium plus, right? Very common ions. And same thing with other metals such as magnesium, right? Has 2 valence electrons. So it wants to lose 2 electrons, and it'll form magnesium 2 plus. So for example, when magnesium interacts with fluorine, fluorine has 7 valence electrons. You can predict that it's going to lose 1 of its electrons, and so the fluorine will have a filled octet, but then it's still got 1 more to lose, and so then you can predict that it will interact with another fluorine and give up another electron here to form our final formula of magnesium 2 plus and then 2 F minuses. Right, and so in this case, they're all happy because they all have a full valence shell. Non-metals also kind of cheat a little bit to get a filled valence shell. Instead of giving or taking electrons, they just say we're going to share our electrons. So non-metals share electrons with each other. So for example, carbon has 4 valence electrons, and then hydrogen has 1 valence electron. And so we can see that carbon is 4 electrons short of an octet, while hydrogen is only 1 electron short of an octet. Remember, hydrogen doesn't actually want an octet. It wants a filled valence shell. It only has the 1s orbital, and so that'll only be 2 electrons, right? So that's why I prefer saying filled valence shell over octet rule. And so what you can predict then is 1 is 4 short, 1's 1 short, right? We're going to have 4 of the 1 short. That way our numbers all make sense, right? So we have our carbon with all of these hydrogens surrounding it, and then they all just share their electrons to form some covalent bonds. Right, and so we can depict this like this. And so if we take a look at our carbon, it's surrounded by 8 electrons, so it has 8 valence electrons. And each hydrogen is surrounded by 2 valence electrons, so they're both happy, right? Carbon has 8 valence electrons, hydrogen has 2 valence electrons, and so they're both happy because they both have a filled valence shell. And so you can see kind of how they're cheating because we're double counting these electrons, right? But that's okay. This is what happens in real life. And then, of course, we can take this a step further. And instead of drawing dots, we can just draw lines, right? Where each one of these lines represents a bond. That is 2 electrons, right? And so let's take a look at some other atoms. If we take a look at nitrogen, nitrogen has 5 valence electrons, and so it's 3 electrons short of a filled valence shell or an octet. And so if you think about it interacting with hydrogen, hydrogen is of course 1 short, and then you could predict that there will be 3 hydrogens here. And so when you draw this Lewis structure, what you end up with is nitrogen with 3 hydrogens, and then nitrogen has what's known as a lone pair, right? So these 2 electrons that belong exclusively to nitrogen are what's known as a lone pair. And if you count the electrons, nitrogen has an octet, hydrogen has a duet, 2 electrons, and so they both have a filled valence shell, so they're both happy, right? Same thing here, oxygen has 6 valence electrons. If we think about that interacting with hydrogen, we're going to have 2 of them. And so then we can draw this Lewis structure, right, where this water molecule has 2 lone pairs. And so this is just a very quick and basic review of Lewis structures. This whole course is based on Lewis structures, so you need to really get good at Lewis structures. We'll do a little bit more review, but not much. I'm going to assume that you know what's going on. If you don't feel like you know what's going on, watch some review lectures. I'll link them online. But basically, I'm going to assume that you're good at this. Right, we'll do a little bit more review, but not too much. You have to be good at this. If you can't draw Lewis structures, you're not going to have a good time in organic chemistry. And then don't forget some exceptions. Boron and aluminum, they only want 6 valence electrons, so they have a tendency to form only 3 bonds. And then beryllium only wants 4 valence electrons, so it has a tendency to only form 2 bonds. And then, of course, everything beyond period 2 can break the octet rule, but period 2 cannot. You really need to review the Lewis structures and really get good at them.